So this is our second lesson on probability. Since the basic calculation within probability involves counting the number of outcomes that fit into a particular event, it makes sense to have a tool to visualize and keep track of all of the outcomes in a sample space. We do this by using sets. So we need to recall the basic definition of a set, and that is identified right here. So it states that a set is simply a collection of things. They could be numbers, objects, anything we'd like, that satisfy a well-defined criteria. So we need to be specific. The things that are contained in the set are called the elements of the set. So with exercise number 1, the set A is defined as the collection of all integers that are greater than 0 and less than 10. So we're going to write out what set A is in roster form. So that means we're going to be using set notation. So you'll notice the little brace, our squiggly brace, and then we're going to list out all the integers between 0 and 10. Notice 0 and 10 are not included because we're looking for the numbers that are just greater than 0 but not including 0, less than 10 but not including 10. So that's numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. They're separated by commas, and these are the elements of set A. So part B says to show set A in a Venn diagram. Venn diagrams are just our circles and rectangles and show the relationships between different sets. And in this case, it will be a very simple Venn diagram because all of the elements are contained in one circle, 1, 2, 3, 4, 5, 6, 7, 8, 9. So a subset is any set whose elements are contained within another set. We're going to give two examples. So we're going to give two possible rules that could define subsets of A. So we're still working with this initial set A, either in roster form or in Venn diagram form. We're going to create these subsets, and we're going to write them as sets labeled B and C, and we're going to list them in roster form. So set B is going to be defined as all integers greater than 3. So over here you'll see our roster form, B equals, then we have our squiggly brace, the values that are within our set A that are greater than 3. So that includes 4, 5, 6, 7, 8, and 9. Our second subset is set C, and its definition is going to be just all even integers. So here we are showing in roster form set C, the subset of A is going to be 2, 4, 6, and 8. So there is one question, do sets B and C have any elements in common? Well, they do. They both have 4s, 6, and 8 contained in them. But they also have items that are unique to the subsets. So now we're going to get back to a little bit of probability with exercise number 2. Consider an experiment where we first toss a coin and note the outcome. And then we're going to roll a 6-sided die and note the outcome. That means we're going to record it. So part A states, write a set of ordered pairs such as H, 4. This represents a heads and then a 4. So that represents all outcomes for this experiment. So we want to have a list, and that's what I have here. Open the set of braces, and we're going to list all the possible outcomes. We could get a heads first with a 1, heads first with a 2, heads with a 3, heads with a 4, heads with a 5, heads with a 6. Perhaps we flipped the coin and got a tails. Tails with a 1, tails with a 2, tails with a 3, tails with a 4, tails with a 5, tails with a 6. This is going to be our entire sample space. This set is what we are going to call set S, our sample space. Closing with the brace, and that is all of the possible outcomes. If you need to, pause the video to make sure that you've had an opportunity to write down all of these combinations. Part B, write a set of ordered pairs that represents the event of getting a tail and an even number. We're going to call this set A. So set A is going to be a subset of S, our full list of outcomes. So we want to get a tail and then an even number, a tail and another even number, a tail and another even number. So there are only 3 combinations that will result in what I'm looking for. And so there are 3 elements in set A. Part C, the complement of a set. A complement of set A will be all of the events in the sample space S that do not fall into set A. So a complement is just everything that is a not scenario, which we learned about in the previous lesson. So if we want to write out the complement of set A, we're going to call it set B, but it's going to be everything in the sample space without those that are in set A. So there's going to be 3 less in set B than what was in the original sample space. So you'll notice we have heads 1, heads 2, heads 3, heads 4, heads 5, and head 6, because we, in set A, wanted to start with the tails. So the tails that are included down here are the tails with odd integers, tails 1, tails 2, tails 3, and tails 5. So this is set B. It is the complement of set A. Together they make all of the sample space. So now we're asked to find the probability of selecting one of the items in set A. So the total possible combinations are 1, 2, 3 out of a total of 12 combinations, and that fraction will reduce to 1/4. The probability of selecting a combination from set B would be 9. There are 9 different combinations here out of a possible 12 from our sample space. When we reduce that fraction, we get 3/4. Take notice of what we have for our fractions and what they would add to. A set and its complement are important when we look at probability because all outcomes fall either fall into an event or its complement, but they do not do both. Different textbooks use different notation to denote complementary or complements. Since the notation is not universal, we're going to simply refer to complements by name instead of by symbol. Consider rolling a single 6-sided die. That's your typical die that you play a board game with. And you're going to be recording the results. Let set A be the event of rolling a number greater than 4. And let set B be the complement of set A. So to begin with, we're going to draw a Venn diagram that illustrates the sample space. Sample space is represented by S. And you'll see that we have a big rectangle here, and it's labeled with an S. That represents all the possible combinations. Sets A and B are subsets, and they are complements of each other. So set A is what we're looking for, and that is a number greater than 4. So on a 6-sided die, that means we're only going to be looking at numbers 5 and 6. There's my roster number, and there it is in my Venn diagram. Set B is the complement, so it's every other number other than those that are greater than 4. So we have 1, 2, 3, and 4 in that set, and you'll notice those here. Both are labeled, and they do not overlap because there are no values that fall into both sets. Find the probability of event A occurring. Well, there are only 2 values out of 6, so that reduces to 1/3. The probability of set B, there's 4 of them, out of a total 6, that reduces to 2/3. Again, 1/3 plus 2/3, our combined probabilities are again going to add to 1. And that should always be true, because together they should create the entire sample space. And so that's listed here. The sum of the probability of an event with the probability of its complement will always be 1. Exercise 4. Answer each of the following questions by using the relationship described above. If the probability, I will draw a red marble from a bag, is 3 over 17. So I'm giving you the probability. This tells me that there are 3 red marbles with 17 marbles in total in the bag. So the probability of pulling a red one is 3/17. What is the probability that I won't draw a red marble from the bag? So all we do is take 1 and subtract 3/17. Remember, 1 can be written as 1 over 1, 17 over 1, 17 over 17, or 300 over 300. As long as the numerator and denominator are the same, we have a value of 1. So 17/17 minus 3/17 would be 14/17. You could also utilize your graphing calculator and your MathFrak button. So the probability of not selecting a red marble is 14/17. If the probability that it will rain tomorrow is 20%, what is the probability that it won't rain tomorrow? Well, what we need to do is start with 1, and we need to subtract 20%. 20%, of course, as a decimal is 0.20. So when we subtract from 1, we get 0.80, which is 80%. So there's an 80% chance that it won't rain tomorrow. In theoretical probability calculations, the sets that make up the sample space can get difficult to write out. It is good to remember things like tree diagrams to help. So in exercise 5, we're going to work with a unique die. We're going to work with 2 4-sided die. That means instead of having 6 sides, it only has 4. And they are rolled, and the number on each is noted. So you'll see the tree diagram here that represents all the outcomes in the sample space. So to begin with, I could roll a 1, 2, 3, or 4. So there's 4 possible numbers I could roll the first time. And then, of course, when I roll a die the second time, or the second die, I have 4 possible outcomes there. Well, 4 times 4 is 16. So there are a total of 16 possible outcomes. We could also count all of the little branches of my tree diagram, and I would get 16 as well. What is the probability that you don't get 2 of the same number? So what I'm looking for is all the possible combinations where I don't have a 1, 1, or a 2, 2, or a 3, 3, or a 4, 4. So in each of these groups of the 4, 3 of them are what I'm looking for. So I have 3, 6, 9, 12. 12 of them do not have a repeat number. Out of a total 16 combinations, reduce the fraction, we get 3/4, which is 0.75 or 75%. That is the probability that you don't get 2 of the same number.